board and of course have Mac on board. Mac is the co-founder of Primo, and he's going to be sharing with us the how to fine-tune. He's going to be talking about fine-tuning of LLMs, and basically all you need to know around about fine-tuning, especially with Primo, of course. So before we go on, there's a GitHub repository that's in the chat. So this is just to really help you with the walkthrough. So you can open that somewhere, some other tab, and then during the workshop as well. That's mostly going to be the repository for reference as we walk through with Mac. Mac is going to be sharing a bit more about what Primo does during his talk, and then we're excited to have you on board, Mac, again. So if you're a few housekeeping rules, if you have any question, you have any concerns during the workshop, please leave your questions in the chat. We're happy to respond, and then Mac will maybe occasionally check in, or towards the end of this workshop, check in to see how maybe you can get your questions answered. If you have any other concerns at all, just put them in the chat as well. Would be willing to sort of help support you as you go through the workshop as well. Thank you, and have a great time. Yeah.
Great. Thanks, Stephen, for the introduction. Today's workshop primarily will be involved. We'll figure out how to get the data to actually fine tune on two important parts of it. It's the quantity and the quality of the data, and then actually running a fine tuning job to fine tune a fairly large model. So I want to actually talk about a couple things with respect to the workshop in itself. Everybody should be able to run through the prompt engineering portion, where we dig into a data set and want to manipulate it and synthesize more data. However, actually fine-tuning the model may not be accessible to everyone, just because as the assumption that I have in terms of your runtime, you're going to have to need some pretty beefy GPUs to do that. So on that section of things, you won't exactly be able to run all of the scripts that I'm going to be showing, mostly because you'll need at least 40 gigabytes of GPU VRAM in order to do that. That being said, if everybody would just clone the GitHub repo, so then you can have it locally, and then the first thing that you should do is actually run a Poetry install inside of the repository to get all of the library dependencies that you need for the workshop. Before that, I'm actually going to be going back and forth between slides as well as my code. So I'm going to interleave between the two sections, present some of the motivation as well as setting up like the theoretical foundations that you need, and then actually going and digging into the code to deliver like actual value out of the fine-tuning exercises. So that being said, maybe I'll start off with just introducing myself. I'm Mark. I'm the co-founder of Primo. I have the AI practice. I think that we're in a very interesting time, particularly with all of the language models that are being open sourced, as well as all of the new commercial language models that are being or coming out from the larger enterprises that we see today, OpenAI, Cohere, etc. So part of the talk, what we're really going to do is think about how do we actually leverage language models, in particular open source language models, and customize them for our own purposes. The motivation would be, how do we launch the next million AI apps? So Primo, the company that I founded, is trying to democratize access to language models and allow developers to embed the language models into their production applications. We're going to be launching our product in the summer, so then everybody should have access to it, and hopefully what we want to present to everybody is the easiest solution to fine-tune and serve your models. So to start, some motivation on the different types of strategies and approaches that you actually want to take in terms of which models to choose. So typically all the modeling approaches we have are you have closed source models. Everybody sort of knows GPT-4 and Google has their competitor, Palm 2. You can also take open source models that are fine-tuned, such as StarCoder and Replit. These are two coding examples. And then we have like smaller specialized models that are the traditional models that showed up prior to 2018 that everybody's pretty familiar with. We're not going to go into those, mostly because what we really want is to be able to do generative AI, right? So typically when customers come to us, they question the fact of wanting to fine-tune and customize your own model. So OpenAI is best in class. And certainly you can go to it and think, hey, why don't I just have my open GPT for X model, GPT for legal, GPT for finance, all those type of different domains. That's actually not possible. So it's really only limited to their base models. So most of those are the Text DaVinci flavors, and you're able to hit their fine-tuning APIs, but these are actually not the best of breed models necessarily. These are just models that they present and are openly available, but they are certainly oh, sorry, I didn't know I wasn't screen sharing. Sorry. Yeah, so kind of going back on the slides, apologize for that. We have a few modeling approaches here. I show those. So, in the backdrop, we have OpenAI, or we have a lot of the open source fine-tuned models. We're going to be focusing on Flan UL2 today. It's a pretty powerful model, 20 billion parameters, openly available, open license, and also has been shown to be quite useful for NLP tasks. So, I kind of presented the information of why you can't really use OpenAI. You can only use their older models and fine-tune those, but GPT-4 is just a black box model that you can only run and at best do prompt engineering around in order to get the behavior that you want. But it's not customizable in the way that you actually want for your enterprise purposes. So with respect to why you want custom language models versus closed source models, the important aspect about those are model ownership with respect to having your intellectual property encompassed into a modeling pipeline for that, as well as meeting certain customer SLAs. So you have to meet an SLA to your customer, but your customer doesn't really care if you're relying on OpenAI and they're down for 2 hours or so. You want domain expertise too, as well, in terms of your custom models. So everybody wants to be a master of their domain and be an expert there. So you're seeing a lot of language models pop up that are specifically designed for a set of tasks, downstream tasks. And finally, you have security and privacy. So we work with a lot of clients personally that want to have models governed within their virtual private cloud or on-prem, and they have fairly restrictive policies around where data can be moved in and out of. So that basically precludes them from ever being able to use OpenAI or the closed source foundational models. So just to preface what we're actually going to be focusing on in terms of supervised fine-tuning, for the rest of the workshop, we're going to be doing prompt-based fine-tuning. There's other types like multitask, few-shot, and domain-specific, but the recent literature and the recent set of technology that's been released has shown that instruction fine-tuned models tend to be the best because they can be zero-shot learners for tasks and they understand what you want to do. So in motivating this, I'd like to kind of delve into what we need to think about. Do you think that we can actually just come up with a model and come up with a model and immediately fine tune it on anything. I think that what you actually need to do is you need to start off and select your task properly in order to figure out what proxies and what types of data sets that you need there. So our task framework that we actually use at Primo is to kind of think about things from a knowledge-based task or a reasoning task. In terms of the knowledge-based tasks, you can think about wanting to have a custom model that's really proficient at doing the set of tasks that you would think are pretty basic and necessary, such as name entity recognition, certain basic Q&A, or have it be really well positioned for doing complex tasks, such as those that you would expect from a knowledge worker. And these are actually one of the more interesting use cases that are appearing today. Now, on the reasoning side, we usually break that down between coding and math. So then on the coding side, you either want to generate new code or you want to explain a set of code. So I would encourage everybody to look at Helm, which is an open source initiative, where the Stanford University is presenting and trying to create a living, breathing set of evals for figuring out how to compare across multiple different language models. It's becoming the standard in terms of benchmarking these models and figuring out how they actually do. We can actually just go to the website right now and take a look. So in terms of the results, I would say for question answer, you can look on top, and it's no surprise actually that DaVinci is the best in terms of the few shot or zero shot results. But you can kind of use that to proxy for the things that you actually want to accomplish using your language. Now, what are the actual challenges that come about? So this is the important part that we're going to jump into the notebook in a second. So consider the scenario where you actually have your base model. You typically have two different directions that you'll go towards, and usually you're choosing between quantity or quality in terms of your data. So on the quantity side, you can reach for synthetic data, or on the quality side, you can actually have humans annotate and label the data. Oftentimes on the quantity side, the main challenges are having the wrong format that's not instruction data, or having just poor quality data that's misaligned with your task. And then on the quality side, you'll usually see that it's expensive. So you have too few examples, or you've just spent way too much money for a lot of examples. So how do we actually get around that? Well, what you actually need is a type of data synthesis pipeline in order to generate high quantity data as well as high quality data. So in motivating data synthesis, I want to present a prototype of a data synthesis pipeline that my research team has worked on. So on the diagram that I'm showing, we're going to walk through in the notebook. What we actually want to do is start out with a prompt generator, which will generate the prompts. And this is just a string that's sent into a large language model. And then the inference module itself is a language model. So what the language model is doing is it's just producing completions or responses is the other name for it. With respect to that, this top section from prompt generator to inference module and completions is what we typically would call prompt engineering. So in doing that, it's a iterative process with human being tinkering with the language or the format or the template of the prompt. To actually make this scale or make this an actually automated process, what you can actually do is you send it into a response post processor. In this case, an example could be a processor such as self-consistency. So you're getting a number of completions out of there. And what you do is the post processor will filter out the responses based upon some majority vote. And the majority vote is just like, which is the most common answer. It doesn't actually involve verification yet, but what we want to do is actually get towards the reasoning path. So given the filtered responses, we can actually move that into an evaluator, and the evaluator is actually a reward model that figures out whether or not to run the loop again into the language model to improve the data, or determine if the set of generated data is already useful for adding into the synthetic data set. So it's kind of a recursive loop that happens here. So if you actually want to do some further reading on data synthesis, we have a really good blog post from one of our scientists that covers a wide range of the research and also how to delve into it. That said, let's move over into the notebook itself. So if everybody can go into the prompt engineering notebook, you can start running I'll run through some of the code with you and also explain what's actually going on in some of the steps. With that being said, maybe if anybody has had any problems with installing the dependencies, you could probably send that into the chat and then we can figure it out. If not, I'll determine, I guess, from whatever hands up or thumbs up if everybody's already gotten their environment installed correctly.
I think some people are having problems with installing the dependencies. Is it?
Yep. Does everybody? I think the first thing that you have to make sure of in your poetry environment is that you change the Python version to the version that you have running. So one thing you could do is just do Python version. I've tested this on Python 3.9 and 3.10. I'm not exactly sure if 3.8 will work in this environment. Cool. And if that's the case, I would say maybe in the public repo, you can create some issues in there, and then we can kind of improve the set of dependencies or actually figure out what's going on. Just for the purposes of time, I think we can kind of move on and figure out what to do there. And I appreciate everybody who's sort of interacting in the chat and helping other folks in the workshop figure out how to install dependencies. Typically, what I like to say is the only thing that is getting in the blocker for artificial generative intelligence is Python dependency resolution. So that being said, let's go into the prompt engineering notebook. So I actually already uploaded the set of data that you can work with here. You may have to change your constants file, mostly because maybe your home directory or path or wherever you get cloned is not specifically set up this way. But if you have that all running, you should be able to kind of download the data set. Cool. It kind of seems like most people are getting the dependencies installed correctly due to my bad in terms of the Python versioning. So remember, we kind of have the motivation over here that what we want to do is we want to have prompt generator to generate prompts and feed into a language model. So we're kind of on this step right now. So just run some of the dependency imports. Right here, what I actually have are a set of math questions and answers. And the entire goal of this is for the language model to produce answers to questions that we don't already have answers for. So I'll repeat. Right now, this file is question answer pairs. And we want the language model to generate answers to another file in the datasets that is math questions only. In terms of what to expect, I'll help motivate this by looking at one of these problems. And I already am choosing the easiest problem because reading out these other problems starts to make me confused, like I was during the SAT. What it actually says is James decides to run 3 sprints 3 times a week. He runs 60 meters each sprint. How many meters does he run a week? So the answer to that is 3 sprints 3 times a week, which equals 9. And then 9 times 60 for the 60 meters. So then you have 540 meters. You'll notice that the answer actually provides a reasoning path. So back onto what we wanted, right? We wanted the answers to be provided step by step. And a lot of the literature tends to talk about chain of thought. You can look at that up in terms of all the papers that are written about that. But that is basically what we want. We want to get the rationales and have the language model learn the rationales to produce the correct answer on an unseen question. So the next part that we need to do is we need to, if you run the cell, what we're going to do is that we're going to sample and create our sampling pool of examples that we're going to feed into a prompt. So it's all basically from a software level, it's just string concatenation. So this produces a list of exemplars. So we chose 8 exemplars, and that is because that tends to be the standard in the literature. If you choose too many, what actually happens is you're kind
Hi,
of
Max. Sorry to interrupt. Can you hear me?
Yes.
Just can you zoom in a bit so that it's easier to see your screen?
Sure.
Right. Yeah. Perfect.
Sorry about that.
Yeah.
So this should be a list of 8 now. Interesting. Trying to see if somebody has questions here. Looks like a poetry install. So for those who actually have the environment installed, sorry if some folks don't have it, but you'll get a list of 8 question answer pairs all here. And on this next cell, if everybody run it, we're going to take the math questions that we want the answers for and then pair them with a meta prompt. So basically we're telling the language model, what do we want it to do? So solve the math problem step by step and provide an answer to that. So what do I expect coming out of it is that I will have the actual set of instructions at the top for the language model, and then a set of 8 question answers or problem answers with an answer blank at the very end. So the question that we actually want answered is this one. Dax went to their farm to pick some apples and found half as many bugs as ants in the garden. There are 50 ants, calculate the total number of insects in the garden. So we expect the answer to be produced from here. Here, I would actually ask for everybody to change the base model if you're running it locally. So I would say you should run Google Flan P5 small. So that's probably one of the smaller models that you can download and actually run locally. But in my case, I actually want to show you why you need a really powerful model. So it'd be interesting to see, maybe some folks can post the responses for what's actually generated soon. But here I'm just loading Flan UL 2 into memory. And it's, to be frank, it's going to take a little bit of time, but it's a 20 billion parameter model. So at half precision, which is 2 bytes per parameter, it's going to occupy about 40 gigabytes of memory. So if you all are running on CPUs, it won't be as much of a problem. The only main problem is if you're running on GPUs, you're going to get CUDA errors if you don't have enough memory to support this model. So as it's just loading the shards, I'm going to look into the next set of cells for the code to generate the completions. So what we're doing right now is I'm going to be generating, so I'm going to be providing the configurations for the model to break down the prompt string that I have, and then generate the set of code, generate the set of responses that I want there. So as you see, we have the shards are loaded, and then I'm going to just run the inference module part of our pipeline. So the inference module is the language model itself. So give it a little bit of time. LLM inference is a known problem today, so probably it's going to take a couple seconds. Cool. So if we look at the answer to the response, if there were half as many bugs, the ants in the garden, there were 50 divided by 2, 25 bugs, total number of insects equals 25 plus 50, answer is 75. Let's go back on the question. I just want to double check that it's sensible. So, you're trying to get the number of ants in the number of insects in the garden. That's actually fairly sensible, right? What it did is it provides not only the set of the correct answer here, the answer is 75, but it also provides like step-by-step the intuition or the rationale for figuring out the answer. Just to bring us back onto where in the pipeline we are. So we've just created a prompt. We sent it into the inference module, and then we've generated responses. So in our case, we're actually just generating one response. I could run this. So in actuality, when we internally at Primo, when we are generating new data, we have to run this language model 32 times per set of problem question to generate, a set of 40,000 data points. That's going to take a little bit of time, and we don't really have hours to spend on this particular exercise. But this kind of gives you a sense of like what you need to run in this pipeline to get like a singular answer with rationales out of it. So we have to create a contrived example here, mostly to demonstrate the self-consistency element. So assume that, suppose we had 4 answers being generated from the above pipeline. So in this case, here are like a set of 4 answers with the reasoning paths here. The whole point of this is actually just to get a majority vote. So which is the most common answer? So that involves pre-processing the string and then choosing or filtering out the non-majority answers. So you get the majority answer, which is typically the right answer if you have a powerful enough language model. But it would be interesting to see for you folks when you're running it, when you do flan T5 small, if it's just outputting nonsensical completions because it's just not powerful enough. That would be my presumption. So here are kind of the list of completions that we're working with. And you'll notice that 24 clearly is the correct or the majority answer. So all we're trying to do here is just get the list of completions, and then we're going to create a dictionary for separating out the completions that have a answer of 34 and the completions with an answer of 24. So it should be a 3-to-1 ratio in the dictionary that's being produced here. So that is doing the part where we're finally going to move into self-consistency. So we have the set of answers and we just want to filter it out. So looking back on the post processor, we're getting the filtered responses. So in this case, we went from 3. So we get 3 responses where we began with 4 responses here. So that's kind of the whole point of it. How do we filter out the nonsensical completions that we either don't want the reasoning path for or aren't really useful for us? Now, the final part of the pipeline is the evaluator. And this is kind of the most tricky part. So the important intuition behind that part is that we want to get a diversity of responses to increase the complexity of the data set. So RougeL is a statistical measure for the amount of overlap between strings. So in this case, what you'll see when I run this cell is that we're taking a candidate and reference set of sentences. So they both semantically mean the same thing, but we're comparing them to each other to figure out which one has the least amount of, basically the least amount of content for the most amount of semantic meaning. So the point of that is language models want to have more diversity in their set of reasoning paths in order to be able to, in correct reasoning paths, in order to be able to learn better. So this is the evaluation step in which we are trying to choose the set of completions that we actually want to keep in our synthetic data set. So on this part, what we're actually doing, if you run this cell, is we're getting the average pairwise Rouge scores. So here is each part of the list here, 0 and 1, are actually the Rouge L scores in comparison to this sentence with every other sentence and taking the average of that. And then here's just the average of the average. So pretty meta there. Finally, running this cell, what we get is what we expect, which is a very important distinction here. So this sentence says, "Hi, it's nice to meet everyone," right? And what are we comparing there? Why did we keep that particular sentence? There's "Hi, it's nice to meet everyone" versus "Hi, everyone, it's nice to meet." It's a little hard to specifically kind of catch the difference, but the candidate sentence object here is actually a little bit more fluff versus the reference one. So it's, shorter. So the reference one actually contains more meaning, which is "it's nice to meet," right? Whereas the one above says "it's nice to meet you" as well. So you're taking the substrings here and then figuring out which parts are overlapping between the two, and then creating a metric that shows diversity between those. So in this case, right here, we're filtering out the Rouge scores that are too high, because a really high Rouge score just means everything is clustered together and we're not getting good diversity in our data sets. So that's kind of what we're doing here. And with the Rouge evaluator, we now can see, the Rouge scores for all of these data sets. I'll kind of move on because, for the purpose of time, I want to get into the fine-tuning element of things. This notebook, everybody can kind of use to play around with, send your own completions to. Particularly, it's well-suited for math right now. But I've generated, before everybody got here, I've also already previously generated a bunch of GSM 8K GSM 8K synthetic data. So I take the original GSM 8K data and then I synthesize more data on top of it and improved it for the Flan UL2 model. Kind of brings us into the next step of the workshop. So I think everybody probably across the entire community is very interested in supervised fine-tuning. We already have now demonstrated that we can take data and actually get more quantities of data and higher qualities of data as well. But I want to motivate our discussion by presenting an example of why it's important to count, the amount of memory that you have at your disposal. So when you do naive data parallelism, let's do some back of the envelope calculations. If you have a 15 billion parameter model, you're going to have to hold 2 bytes per parameter in the model in half precision. And then you actually have to keep a master copy of the other parameters in full precision, which is 4 bytes per parameter. And then if you're using Atom, which is the workhorse optimizer for basically all of training for deep learning gradient descent, you're going to have to keep 2 variables, momentum and the running average, in memory as well in full precision. And then you have 4 bytes, which are must also be 4 bytes per 15 billion parameters for all the gradients. So this doesn't include the activations, but you're already running at a total of 270 gigabytes of VRAM. You can look up the cost of A100s right now online. They're pretty expensive. So we need a way of really reducing the amount of memory footprint in these models. So what does that actually look like in terms of all of the breakdown of memory? In terms of the activations, you're going to expect 25% in the activations, 25% in the model parameters, and then 50% in the optimizer. I can illustrate that in a second, but why does that matter? So you have a huge language model where all of these things are sitting into memory, and what's the whole point of attention? Attention is trying to provide more context, right? Like if you remember what attention is defined as, it's like the cross product of all of the context you pass in. So the context is just the huge string or the prompt that you're giving a language model. And then you're taking like a cross product of every token in that prompt to every other token. So that is why sequence length is actually a memory killer. So even though you can increase your batch size, the moment you increase your sequence length, the amount of memory footprint goes up quadratically. So I actually took the Math GSM 8K dataset and then plotted a distribution of the token lengths here. Luckily, we're okay in our instance because most of the tokens, as you can see, are less than about 256 token length. That's going to come back to us in a second, where let's take a look at the dataset itself. So let's open up the notebook, actually, for the GSM 8K pre-processing. If everybody's able to go to this notebook, I think that it would be useful to kind of dig into the data itself. So if we can run this cell, you'll see in this instance, you'll have to change the model path. If everybody else was using Flan, if everybody wants to use a different model, such as the Flan T5 small, which maybe you downloaded previously, this is basically the line that you'll have to change. I already have the data downloaded, but if you don't have the data set downloaded, you can change the data set in here in the data files into a different data path. So in this case, it's the Math GSM 8K dataset. If you look up on Hugging Face datasets, you basically just have to point to that path to download the dataset in memory. But let's just take a look at the data itself and then consider why I want to cut off the token length in order to facilitate better processing in memory. So you can run it here. I'm going to download the dataset. It's already cached in my instance, so there's not much I need to do. Take a close look at the preprocess function. In here, the most important parts to note are the max lengths. So I'm basically, you can't have generally in matrix multiplication, you have to have a consistent length in your tensor, right? Like each row can't be a different length in a tensor. Otherwise, it's kind of a weird shaped matrix. So in our case, I want to cut down to 256 tokens at most. And then for the ones that are too short, that's why I have padding. I'm going to pad them. And basically, you're going to see a bunch of, I think, negative ones for the padding token or negative 100. And then for the ones that are too long, I'm just going to cut them off. You can use a different preprocessor where you actually extend the tokens to be one long set of tokens where you don't cut it off, but that's not really within the scope of this particular discussion. So I'm just going to run this, and using Hugging Face's datasets, I can just tokenize the dataset really quickly. So let's take a look at the question here. So again, this is the Math GSM 8K dataset that we synthesized, and we have a bunch of questions here. there are numerous other questions if you want to look at the first 5. Then that's the raw data set. Let's look at the tokenized data sets and see kind of what's going on here. So in the tokenized data sets, as you can see, this particular, the first question answer that we have here, or sorry, this is the first question, is shorter than the 256 token length. How do I know that? I know that because, as you can see at the end, in our case, the padding token is just 1. So it's just adding all the padding into the tensor so that when I pass it into the large language model, it kind of considers this as a null token. If you've kind of heard of end of string tokens or padding tokens, that's the intuition behind all of it. You're just mapping empty space, or you're mapping out of vocabulary tokens into a particular numerical embedding or a number. So I'm going to go back to the slide for a second to talk about what's actually going on and how we're going to get across the problem of the CUDA error. So I'm actually going to go over to another part of the workshop where I have a script here. So you guys don't need to exactly know the exact details of every part of this script, but if you look at it, what I'm actually doing in the script is I'm just running the pre-processing, and then I'm going to run exactly what I showed on this slide. So naive data parallelism here. Sorry, yeah, naive data parallelism without LoRa. So I have to run this as a script because I need a launcher in order to do that. But if you take a look, I want to show you the number of GPUs I have running on this virtual machine. So I'm running on 4 40 gigabyte A100s cards. So this is an extremely beefy runtime environment that most people just don't have access to. And it is going to even not be enough for me to run fine tuning on our synthesized data set. So if you look into the README that I provided, you'll see the script that you need to run in order to accomplish this. So wherever you have the model path, so the end of here, this is going to be the local model path of the model that you want to run. But in our case, it's going to be Flan UL2. And I'm going to be using some naive parallelism in order to run this. And as you can see, it's going to kick off a job. Oh, sorry. I actually kicked off the correct job that will not have an out-of-memory error. But in this case, spelled that incorrectly. All right. So in this case, I'm actually going to be running a job. There is a really useful command that you can run to profile your data, and it's nvtop if you have that tool downloaded. But right here, you can already see that it's loading the model shards into memory. And what DeepSpeed, so the library that I use is a Hugging Face accelerate to launch this job using naive data parallelism. And it pre-allocates the set of memory that I need in order to accomplish the job. You'll see that it's almost at 100% already, and it's just loading in the model. And it's going to basically have an out-of-memory error fairly soon. Yeah, so someone put in a question, is it using all 4 GPUs without having to code for parallelism? It is actually using all 4 GPUs. Accelerate's very easy. I'm not going to go into the exact code, but what everybody should note is the training loop over here already takes care of all of the parallelism that you need. So the main thing that you need to change locally if you want to run this job is to change the number of machines. So if you just do one process, it's just going to run in a single process, assuming that you can hold the entire model and memory on your local environment or whatever runtime environment you're using. And then we're using beat speed in this case. I'm just going to put it back to 4 in order to accomplish this. Let me just check that all the memory has already been freed up from this entire process. So I'm just restarting the kernel so that what I want is this to all go down to 0. Cool. We're getting zeros across the board in terms of the memory, except for this amount of memory that's being occupied on each card is actually literally because of CUDA itself. It takes a little bit of memory. So as you can see, if we look at the stack trace of what just happened, right, you should see a CUDA error. And this is what the accredited deep learning community is always extremely upset about, and why we have, effectively a GPU shortage. There wasn't enough memory. It tried to allocate 3 gigabytes of memory when only 1 gigabyte of memory was free. So this is the entire, change everything here from 15 billion parameters to 20 billion parameters, and that is what's going on. You're having out-of-memory errors because you're using naive data parallelism with mixed precision, and you're not using parameter-efficient fine-tuning. So what is our solution? I'm sure everybody has sort of heard about parameter-efficient fine-tuning in the community these days, but specific technique that we want to use is LoRa, which is a low-rank adaptation method. So basically what it's doing is it's taking the set of data and assuming that you can dimensionally reduce the weight matrix and learn the weight matrix on like an incremental basis. So it freezes all the previous weights in Flan UL2. I have a previous presentation that actually goes into this in a little bit more detail. We're actually going to go into it in a practitioner standpoint and run the script that will achieve LoRa fine-tuning. But for the purposes of this demonstration, I don't need to motivate, kind of the other parts of it. The main thing that you just need to know is that the loss function that we're actually trying to optimize, you can separate out the frozen set of parameters with the the low rank parameters. So you have the pre-trained weights here, and what we're trying to do is we're trying to freeze the pre-trained weights, and we're trying to learn the new set of weights on the training data that we're going to send over to Flan UL2. So a few caveats I just want to get across the board. Mostly this is only applied to attention layers. You may have heard of a new technique called QLoRa that actually does 4-bit quantization and runs LoRa on every single layer. I'm not going to get into that today. It's outside the scope of this demonstration. But for LoRa, at least, it's been shown that you can actually use this technique to fine-tune and perform even better than full fine-tuning. So full fine-tuning was the instance that we just showed on the command line where you had out-of-memory errors. And that's when you don't do any sort of freezing of weights. You just allow all the weights to move around while you're optimizing, and you have to hold everything in memory there. So what are we going to expect? So I'm going to show you the memory profile of what's going to happen when we actually do the LoRa parameter efficient fine-tuning. But, let's just have back of the envelope on our mind amount of memory that's going to be occupied using LoRa as opposed to the full fine-tuning. So it's going to be about a 68% reduction in the memory footprint. So this is when we load the model. As you notice, like even upon trying to load the weights of the model, you're getting towards 80% of the memory inside of the model, right? So if we go into here, what we'll see is we don't have anything in memory yet, and we're going to run this script on the correct LoRa fine-tuning. So in the fine-tune folder, you'll see that you can run the deep speed accelerate script that does parameter efficient fine-tuning. And what's kind of great about it is we're just leveraging Hugging Face's PEFT library here, and it's a one-line change. So if you do a diff on the two files, you'll see that all you actually need to do is to add this part. So you have PEFT. So in our case, R is a parameter that, like, the larger the R, the more weights you're going to have to learn. So the more memory footprint you're going to use. And then drop is just tends to be a parameter I don't really change that much, and it doesn't really do much of a difference for our fine tuning. But then you just need to call what get PEFT model actually does. It's just unwrapping the object and then making sure that you use torch.nograd on the set of parameters that you don't want to fine tune. So I'll just launch the script because it'll take a little bit of time to do. It's kind of fun actually for me because whenever I start getting angry and having CUDA errors, I can kind of memory profile it. So it's kind of useful here. So I'm running deep speed with the launcher configs here. This is specific to Hugging Face Accelerate. And I want to note that I'm not using CPU offloading. So what CPU offloading is like when you're about to run out of memory on the GPU, you just actually move the weights into your CPU, but you take actually a significant memory hit doing that. Cool. It actually seems like some stuff is happening right now. Weights are getting loaded and it is occupying all that space. So let's see if it will run successfully. So it's going to take a little bit of time. It's already loaded all the shards into memory, pre-allocated all that memory, and then it's going to run a bunch of data on it. And for those that actually have the luxury of getting many more GPUs than I was able to get here, all you have to do again is just change the number of processes here. So presume that you have like one virtual machine. In this case, I'm running on GCP to do that. So while it's doing this entire process, I'm going to go back and just compare the chart of the set of memory footprint that we'll actually see. So when you use LoRa, you're actually significantly reducing the amount of optimizer memory footprint. So we have different batch sizes, but these are proxies. So in the activations again take up a lot of the memory. So the activations are like the set of contexts and tokens that you pass through the model, and then the forward pass. So like the same thing as saying, I want the model to generate completions. Those are a lot of the memory that's been being taken up by the activations. And then you have 45% of the memory being taken up by the parameters themselves. So that's why you see like this huge set of memory being allocated here in terms of the parameters. So my GPU utilization is actually not that high, which is not the best. I should have optimized this a little bit more, but some tooling and advice for everyone out there. After it's actually running right now, so it's running 15 out of 748 iterations in the training cycle. So I ran deep speed 03, which is a type of parallelism that shards the model parameters, the optimizer states, and also the gradients, all in GPU memory. Even in doing that, what we see is that the yellow line here is the memory footprint. So like how much memory is being occupied during this exact point in time. And then the blue line is the GPU computation. So basically the ideal state is if the yellow line is almost at 100% and the blue line is also tracking it almost at 100%. This means that all the memory that's being occupied at every given moment is being used in a calculation. So that's kind of the whole point of all of the stuff that you hear about parallelism in parameter efficient fine tuning, it's to fit everything on the set of cards that you have, as well as being able to run everything in memory, run all the computations in memory. If you want to read further on more memory usage kind of tricks, we have a blog post out there that actually gives a really good set of back of the envelope calculations and allows you to kind of heuristically define how much memory you need to train certain models. Well, that's basically it for what I wanted to chat about. I'm going to kill this process right now, but I set a notebook for everybody to look at as well. This is just the code to enable you to take what we just fine-tuned. So suppose we finish this fine-tuning job, and then load the set of parameters into memory. So in this code, if you run these cells, what's actually going to happen is it's going to load flan ul2 first in this step, and then it's going to load the LoRa parameter weights that were being learned in our fine-tuning job in this step to be able to attach them to this model. So now, you know, flan ul2 had its original set of knowledge, and now we are teaching it to perform specifically well on the math reasoning data set that we synthesized before. So that's kind of the entire exercise that we're going through. With that being said, kind of rushed through the end of the workshop, but I'd like to open it up for any sort of questions that people have.
Hi, Mac. I think it's been a really insightful workshop so far. I don't think there's been any question that you haven't answered yet. A lot of things has been troubleshooting in the box.
Seems like it's mostly runtime errors and environment errors, unfortunately.
Right. Yeah. Okay. I think a few questions are coming in. And this question is from Pedram. And Pedram asks, are there limitations on using different GPUs together? Say, if, for example, you're using the NVIDIA H100 and A100, you know, is that bad practice in this case for fine-tuning?
Using heterogeneous hardware is not bad practice. It's just difficult. Like, with respect to that, what I mean is a lot of the frameworks like DeepSpeed, they just use kind of heuristics to be able to move the memory around for your model, but it presumes that every single card or the GPU chip is the same. So you may have to roll out or monkey patch some of the code inside of the framework to facilitate that.
Yeah, all right, fair enough. And yes, so even there's a Slack channel. So I'm just gonna post the link to the Slack channel in the chat, so you can join the MLOps community Slack. And I think there's a channel there for the LLM production conference too, so you can join in and ask all your questions. I think most of the speakers will be there. And of course, the next question is, can we get more hardware?
Yeah, I mean, there are third-party providers out there like Lambda Labs and Weave that you can kind of use, but at this point, it's so saturated, honestly, that it's kind of hard to get hardware no matter who you are.
Yeah, that makes sense. So all the comments are, in fact, comments on the workshop. I think it was super executed well. It was executed pretty well, and I think that's it. So if you have any other question, please join the MLOps community Slack. And if you have comments as well, I think Mark is also in the community, so you can tag him, and potentially, if he's available, of course, he'd be willing to get to that question, to your question. And Mark, could you probably tell us a bit more about Primo, if that's something you want to
Yeah.
do.
Yeah, sure. So specifically, our company is going to be offering APIs for folks to fine tune and serve models. So basically, it's going to be kind of a managed platform. The main point of all that is to show you probably don't have to go through all this trouble per model, per instance, per whatever, in order to develop your applications on top of it. So I think that my experiences with all of this is that the last mile kind of effort to be able to productionize applications tends to be kind of hard. So most people just want to leverage the models and the completions and know that your inference is going to happen really quickly. So you notice that even when we were trying to do the synthetic generation, it took a little bit of time for FlawNUL2 to generate one set of answers for our prompt, right? Now imagine trying to do that 50,000 times. It's kind of hard. So we're going to try to democratize this access and this to all these models for everyone and have developers be able to use that.
Yeah, that's awesome. And also, what are the trends with I think self-hosted LLMs these days? I think most of the tools are coming out there. What's sort of your take on self-hosted LLMs versus using a platform that really streamlines the deployment process?
I kind of think, obviously there's a new stack emerging out of the entire landscape, but me personally, I don't. It's not my greatest joy to try to set up all the machines and specifically have the exact batch size or the sequence length correct. There was one more optimization that we could have done on FlawNUL2 that I didn't show, but you can monkey patch the attention layers and try to use flash attention there, and that will help reduce the memory footprint to be able to train more and larger batch sizes. But the open source stack, I think, is something the community really needs, because people need to be able to create their own custom LLMs. But then it's just kind of being blocked by the fact that the infrastructure is too hard to spin up, or you just can't even get GPUs, right?
Right, absolutely. Thank you so much for sharing. Well, I think that brings the workshop today to a close. Again, if you have any question, please ping Mac in the MLOps community. Just type in mlops.community. You should be able to see more details and joining the community, podcast, and every other thing. Otherwise, wish you a great time for the rest of the conference. All right, bye.
Cool. Thank you.
Thanks, Mac. Yeah.
Thanks for everyone for joining. Bye.